Let's take a look at some examples using the logical operators that we've considered so far. Okay, so we've had a look at three logical operators: the AND operator, the OR operator, and the NOT operator. What I'd like to do is to actually look at what are called De Morgan's laws, and these are laws that associate different Boolean expressions together and say that they're essentially equivalent. The nice thing about De Morgan's laws are that they incorporate each of those different logical operators we've been looking at. So first of all, let me state what De Morgan's laws are, and then we'll look at a way to actually prove that these expressions are equivalent using truth tables. So we've got De Morgan's laws. Okay, so for De Morgan's laws we're going to consider propositions. So let's say that we have two propositions, P and Q. And we're going to form a Boolean expression using those logical operators and incorporating the propositions P and Q. So the first expression I'm going to look at is the following. We have P and Q, and then I'm going to take the negation of all of that. Okay, and the next expression I want to look at is the negation of P or the negation of Q. Okay, so we have two expressions here, two compound statements. The first one says take P and Q and then negate them. The second one says negate P, negate Q, and then use the OR operator to combine them together. And what we're going to show is that these two expressions are equivalent. And we're going to do that by using a truth table. Okay, so let me just scroll down here a bit and we'll draw the truth table for these two expressions. So for the truth table, what we're going to do is consider all of the different combinations we can have for P and Q. So let me create a column for P, and let me create a column for Q. Okay, and we've seen that with P and Q, either of them can take on the truth value true or false. So in total we've got 4 combinations. So let's write these down as, say, false, 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 true, true, false, and true, true. Let's also create some extra columns in our truth table. So I'm going to create 2 more here. One for not P and one for not Q. Okay, let's populate these columns then with the correct truth values. Okay, so for the first row here, we have that P is false, which would mean that not P is true. For the second row, we have that P is false, which would mean that not P is true again. For the third row, we have P is true, so not P is going to be false. And for the final row here, we have P is true, so not P is again going to be false. Okay, so to populate the not Q column, let's have a look at the Q truth value. So in the first case, Q is false, so not Q will be true. The second row, we have Q being true, so not Q will be false. For the third one, we have Q being false, so not Q will be true. And finally, we have Q containing a truth value of true, which means not Q will be false. Okay, so these are going to be useful when we're actually going to prove De Morgan's laws. The next column I'm going to put in my truth table is going to be looking at what's the value of not P or not Q. Okay, so we've got here not P or not Q. So to actually figure out what the truth value is associated with this column, we need to look at the previous two that we filled in. So not P in this case is true, not Q is true, so not P or not Q is going to be true. In the second line then, we have not P is true, not Q is false. We form the the disjunction of those two truth values. So not P or not Q, we will again have true here. So recall, for the OR operator, as long as one of the values we're operating on is true, the result will be true. So likewise, in the third row here, we have false or true is going to be true. And finally, we have false or false, and that's going to be false. Okay, so we formed the expression not P or not Q. Let's have a look at the idea behind P and Q. Okay, so to determine the truth value of P and Q, we're going to have to look back to the first two columns here. So for the first one, we have false and false. That's going to be false. The second row, we have false and true. That's going to be false. The third row, we have true and false. That's going to be false. And finally, we have true and true. That's going to be true. Okay. The last column I'm going to put into my truth table is going to be negating the one we've just done. So we've already considered what P and Q is. Let me negate that value. So we're looking here at the previous column, and we're going to negate whatever the given value is here. So not false is going to be true. Not false is going to be true again. For the third row, not false is true. And finally, we have not true is going to be false. So what we need to do then to prove De Morgan's law in this case is to have a look at this column here and compare it to this column here. So for the first row, we have a true in the column that's specifying the OR operator, and we also have a true in the last column. So in this case, the values are equal. In the second row, we can see that we've got equal values as well. Also in the third row, we've equal values, and finally in the last row, we've also got equal values. So for any two given inputs for P and Q, so we can take these as the inputs existing in the first two columns, the result of negating each of those two initial inputs and then using the OR operator is equivalent to first using the AND operator with each of the two inputs and then negating the final result. So this truth table proves that De Morgan's law holds. Okay. So let's just write that out again. So De Morgan's law we have that not P or not Q is equivalent to first take P and Q and then negate that value. Okay, and as an exercise, there is a corresponding De Morgan's law switching the operators. So what I'd like you to do is use a truth table to prove the following. Not P and not Q is equivalent to P or Q and then negate that final result. Okay, so do attempt that as an exercise.